Welcome back. In today's lecture, I am going to talk about the infinite dimensional optimization. Okay, and what we have seen in the previous class that I have some kind of function, okay, and I have to extremize that function, okay, and whatever extremization point that comes into picture, that is some kind of numbers or tuples of numbers. Okay, so if you see clearly, then in order to talk about finite dimensional optimization problem, we have to minimize a function. Okay, function might be multi-valued. Okay, and here means argument of the function might be x1, x2 and xn. So I have x1, x2 up to xn, and here I have fx. Okay, and I am assuming that f map from Rn to R. Okay, whenever we are going to extremize this function and suppose that maxima and minima exist, at that time it is possible to show that whatever quantity that comes into picture, so this function is become minimal or maximal at certain point, and that some kind of tuples of numbers that comes into picture. Okay, so and since if I have tuples of number, then I can represent that space using finite number of bases. What does it mean? That suppose if we are in two-dimensional space, okay, so in two-dimensional space I can represent any quantity by x and y. So I can also write this as a x 10 and plus y 01, like this. I can represent any point in this space by just changing x and y. Okay, so you can see that with help of these two vectors, okay, these two linearly independent vector, I can able to span the whole space. Okay, and due to that reason this is called two-dimensional space. Similarly, I have xn, so n number of tuples of vectors, okay, are required basically to span the whole space. Okay, so that independent vectors are called the basis. Okay, so basis, whenever we are talking about the basis for the optimization problem like this, okay, so that is always come like finite. Okay, and due to that reason name is finite dimensional optimization problem. Optimization means I am going to search about maxima or minima. Okay, now in this problem I have two different class. One class where there is no constraint. If there is no constraint, so we have already seen that I can move in any direction. Okay, but if I have constraint, because in order to find maxima and minima I have to check about all nearing vector. Okay, suppose that this is the local minima, so I have to see the situation of this nearing vector, so I have to move from here to here. Okay, so movement is not restricted if I have unconstrained optimization problem. Okay, if I have some kind of constraint optimization problem, then this movement from here to here, that is restricted. So we have already seen, and due to that reason we have two different classes of problem, that is constraint optimization problem or unconstrained optimization problem. In the previous class what we have seen, that one can able to convert constraint optimization problem into unconstrained optimization problem with the help of Lagrange multiplier. Okay, we have already seen, and again in order to calculate the condition we can able to do the first order approximation. Okay, now in today's lecture we are going to proceed towards the infinite dimensional optimization problem. Okay, so now in infinite dimensional optimization problem I have some kind of functional. Okay, functional is nothing but functions of function. Okay, and if you are going to maximize or minimize that, then now you are not going to get the tuples of numbers. Okay, so now you are going to get some kind of function which is going to give the maximum and minimum value of this functional. Here you are going to get some kind of tuples of number which is going to, if you substitute that number inside this function, then you will get some kind of maximum and minimum value. Okay, but in case of infinite dimensional optimization problem, whatever argument that is in form of function. Okay, so now if you see the space, so that is some kind of vector space. Okay, and element of that vector space now do not looks like this, do not looks like column vector where every things are real number. Now a space is looks like the some kind of function. Okay, function may be in this form, maybe in form of matrices, that it doesn't matter. Okay, but each and every element of this space V is now a function. Okay, and we are assuming that again that map to real number, because I have very special class of functions of function that is called functional, if that will map to some kind of real number. So very specific class of transformation you can tell. Okay, that is going to map to some kind of real number. Okay, so I hope that you are able to understand the difference between these two. Now whenever we are going to talk about functions, okay, so functions can represent by infinite number of bases. Okay, in order to check that, what you can do, you can take some function fx. Suppose this is continuously differentiable function. Okay, so I can able to represent this function. Suppose this function is called analytic function, then I can able to do the Taylor series expansion. So I can able to represent alpha 1 x, alpha to x square. I have done Taylor series expansion about the x equal to 0. Okay, so you can see here that in order to represent this function, I need 1 x square, x cube, x power 5, like that, x power infinity. So infinite number of bases are required to represent this function. Okay, so any analytic function can be represented with the help of this basis 1 x square. Okay, similarly if you do Fourier series expansion of some function, again some kind of cos sin x, cos 2x, sin 2x, something like that, that comes into picture. Okay, so number of bases here is infinity. Okay, and due to that reason, this word like infinity, infinite, that comes into picture. Okay, so I hope that you are able to understand that finite dimensional. Okay, so point where maximum or minimum point that comes into picture, they can be represented with the help of finite number of bases. Okay, here infinite number of bases are involved. Okay, now let us try to see the restriction whenever we are moving from finite dimensional optimization problem to infinite dimensional optimization problem. Okay, now one more important point here I am going to highlight, that there is no need to worry about the constraint optimization problem, because we have already seen that if I am able to embed the Lagrangian multiplier, then constraint optimization problem is converted into unconstrained optimization problem. Okay, so now just we have to worry about the different setting here. In place of Rn, now I have some kind of vector space, and vector space, element of vector space is now function. Okay, so whenever element of this vector space is function, then now we have different possibility. Okay, so in finite dimensional optimization problem, we know that inside the space, okay, whatever function we have defined, argument of that function is some kind of real number. Okay, so unlike, due to that reason I have written, unlike the case of Rn, there doesn't exist a universal function space. Okay, so this function means because whenever we are defining the functional, so that is function of function, so whatever argument of that function, that is coming from some function space, and function space I can define in many different way. Okay, and due to that reason, many different choice of V are possible. Okay, so we are in this lecture, we are going to see that what kind of different choices basically comes into picture. Okay, and if we have different choices, obviously it might possible, if I will take some kind of choice, then maximization or minimization is possible, otherwise not possible. Okay, and after that, whenever we are solving the infinite dimensional optimization problem, since I have infinite many choice, due to that reason I have to clearly specify that what kind of desired space we are going to consider. Okay, so due to that reason I have written that this is the part of the problem formulation only. Okay, so in case of finite dimensional optimization there is no need to worry. Okay, Rn is there, but in case of infinite dimensional optimization problem we have to define carefully what kind of a space we are going to consider. Okay, it means that whatever vector space where how basically functions are going to represent. Okay, now another issue is 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 that whenever we are defining the local minima or maxima, suppose that I have some kind of minima here, local minima here, then we are going to see the vicinity. Okay, so I have to define the closeness. Okay, how close we are. Okay, so at least I need two functions. Okay, at that time we are we are needing some kind of tuples of real numbers. Okay, in case of finite dimensional, but here we need two functions, because if this function is going to minimize this functional j, so I have to check on the both hand side. Okay, or in whole neighborhood of this. Okay, and due to that reason somehow I have to define the vicinity, means this function, suppose that f star is going to minimize this j, so how to define some kind of function in the vicinity of this function f star. Okay, so for that we need some kind of notion. Okay, now another thing, what we have seen that, recall that the definition of local minima, a ball of epsilon with respect to a standard Euclidean norm whenever we are talking about, then at that time we are assuming that element in form of column vectors, and that is nothing but some kind of real numbers. And after that distance, whenever we are defining the distance, at that time we are defining the distance, suppose that this point is x1 and y1, then we are defining distance like x1 square plus y1 square, like this. Okay, so this space is called Euclidean space. Okay, so in Euclidean space it is possible to show that I can able to define some ball of radius epsilon. Okay, and that is actually telling about the closeness. Okay, and that is nothing but the norm. Okay, and how basically we are defining the norm, I will tell you in the here, that suppose if I have some kind of vector x1 x2 x3, okay, up to xn. So these are my vector. So a space I am going to consider that a standard space Rn. Okay, it means that each and every element in this space is represented by tuples of n real numbers. Okay, after that, in order to define the norm, what basically we are going to do, we are going to check three property. Okay, so first property is positivity, and after that we have to check the homogeneity, and then triangular inequality. Okay, and it is possible to show that I can able to define different norm on this space, and due to that reason we are writing generalized norm, that is called LP norm. So LP norm is defined like xi power p, I equal to 1 to n and power 1 by p, like this. Okay, and L2 norm here, if you just substitute p by 2, then that become L2 norm. So in this way we are defining the norm. Okay, and suppose now I have two vectors. If I will take two vectors from this space v and w, then I can able to define the nearness between this vector v minus w, and suppose that if they are going to lie in some epsilon ball, then we are telling that v minus w is less than equal to epsilon, like this. Okay, so what happens that we have very standard way to define the norm. Okay, and with help of that norm, okay, we are able to define the closeness. Okay, but now we are not in this Euclidean space, we are in some kind of a space where functions are involved, so we have to check the norm. Okay, we have to check here now how to talk about distance between two functions, that also is required. Okay, so now let us summarize what kind of requirement I have. First I have to identify that how basically functions are represented in some space, vector space. Okay, so that is first problem in infinite dimensional space. For finite dimension, that is obvious, everything is real number in form of column vectors. Okay, but here we have to make sure that how basically element are arranged. Okay, second problem is that how to define nearness, because in order to show that some point is minima or maxima, I need two function which is very close to maxima and minima. Okay, and for that we need some notion of ball. Okay, so I need, in order to define that ball, I need the notion of norm or norm linear space, you can tell. Okay, and after that we have to also talk about the convergence. Okay, because finally whenever we are talking about maxima and minima, that point is not known to me. Okay, so some way we have to make sure that there exists some kind of convergent point in that space. Okay, so we have to also clearly identify the space. So here in finite dimensional space I have Euclidean space, so everything is very simple. Okay, now let us try to identify the space whenever we are going to solve the infinite dimensional optimization problem. Okay, and due to that reason you can see here that I have to talk about function space, I have to talk about norm, and then I have to talk that how to talk about local minima with help of that norm and function space. Okay, whenever we are going to move from finite dimensional optimization problem to infinite dimensional. Okay, so again whenever we are going to solve the optimization problem or extremization problem of function. Okay, so we are going to consider the vector space. Okay, so typical space is a to b and to rn. Again what I am going to assume that I have some kind of a space, and where each element is in form of function. So like real number, now I have here each and every element in form of function, and this function, whenever function, then that is going to define in some interval. So I am assuming that that is in actually defined in this interval a to b. Okay, so it means that you can try to understand like this: fit and t belongs to a to b. Okay, so in this way first element comes into picture, similarly I equal to 2, then second element comes into picture, and I am going to stack that element. Okay, so in this way we have basically defined the function space. Okay, and functional, now functional, what they are going to do, they are going to pick some element from function space, and after that they are going to map to some kind of real number. Okay, so functional is some kind of transformation, you can think, that will take each and every element from this space, and after that that is going to map to some kind of real number. Okay, so now here you can see that I can assume that whatever function here, that is k time continuously differentiable. Okay, so in order to make some kind of vector space, what I have done, I have collected those kind of functions. Okay, I am going to consider those kind of space only where each and every functions are k time differentiable. Okay, so this is called regularity condition. Okay, so if I have this kind of space, then each and every function are k time differentiable. Okay, now it might possible that I can relax it, I can remove this assumption. Just I will consider piecewise continuous function or some kind of measurable function. Measurable function, we are not going to discuss measurable function in this course. Okay, but if you take the advanced course, then you are able to understand. So for time being, please leave it. Okay, another thing that I can able to give more strong regularity assumption, I am going to consider that all functions are infinite many time differentiable. Okay, and whenever something is infinite many time differentiable, then most of time it is possible to show that there exists a Taylor series approximation at each and every point. Okay, so I can able to give more restriction, means element of the function space, and due to that reason whenever I have real number, then we don't have any choice, because x1, x2, x3, xn all are real numbers, so I don't have choice. But here I have different choice. Okay, and based on that choice I have different space. Okay, and whenever we are defining vector space, then I have to define some kind of element. Okay, field, you can see that element means a scalar we have to define. Okay, whole space. So I am assuming that that particular quantity is nothing but the real number. Okay, so whenever we are defining the vector space, those do not have idea of vector space, I have already recorded several lectures on vector space. Okay, and course name is physical significance of mathematical method. Okay, so please go and see that lectures. Okay, so whenever we are defining vector space, at that time we need two operation. One is vector addition and second is scalar multiplication, and after that we have to search the element we are taking from the field. Okay, so those who don't have any exposure about the vector space, just you can assume that whatever underlying element, that is real number. So this function is also defined over the real number. F2 is means this is real valued function. Okay, so in this way we are able to select different space, and I have already told you that why this is infinite dimensional, because if you see this function, okay, so if I have continuously differentiable function, any continuously differentiable function, if that is analytic, so any point, if you take any point, then you are able to write in form of Taylor series expansion. Okay, so what happens, that infinite many terms are associated with that. Okay, and due to that reason, that is infinite dimensional. Okay, so whenever we are now you have to just recall this fact everywhere, that whenever function comes into picture, then that is going to represent by infinite dimensional, means basis involved in infinite number of linearly independent vectors are required to represent some function, some continuously differentiable function. Okay, or if we are not able to do Taylor series expansion, then we have to go for another expansion. Okay, suppose Fourier or something like that, then again I have infinite number of bases. Okay, so I hope that you are able to understand the first situation, that how to select the space. Okay, and dimension of a space is infinity. Now inside that space, I I don't know how to define the closeness, because what we have seen, that suppose I have some kind of functional, okay, and I have to talk about the extremization of this functional. Suppose this is local maxima, then I have to check the neighboring point. For all neighboring point, if I substitute this kind of function, so I have to draw like this, then that become more proper. So suppose I have a space, and this is f star. Okay, so this function is going to minimize this functional like this. Okay, now I have to also look towards the neighboring two functions. Okay, so in order to define the neighbor or closeness, I required some notion of the distance. Okay, and it is possible to show that using the help of norm, I can able to define the notion of distance. Okay, so if you see the vector space, so inside vector space there is no notion of distance. Okay, but why vector space is important? Because if I have some space, okay, and suppose two dimensional space, so just if I identify two vectors 1 0 and 0 1, means basis vector, then I can able to move in whole space. Okay, so if I have a space, then using the help of vector space, I can able to talk about linear dependency, linear independency, span or basis or dimension, these kind of concept. Okay, but there is no notion of nearness, proximity in vector space, and due to that reason we are going to add something which is going to define the proximity or nearness. Okay, because whenever we are going to solve any practical problem, okay, related to optimization, so one function we know that is going to minimize or maximize something, but in order to give confirmation that is going to minimize, I have to check all local function. Okay, so I need some kind of way to measure the nearness, okay, or quantify the nearness, and at that time notion of norm linear space comes into picture. Okay, so norm linear space is nothing but vector space and with norm. Okay, and I have told you that norm, whenever we are talking about norm, then norm is nothing but some kind of function if you take any element from the vector space. Okay, so suppose that now we are talking about function space. Okay, so I have f1 f2 up to fn. So if you select any element from this space and if you are going to club here, then what happens? One real value comes into picture. Okay, and it is possible to show that this is plus. Okay, r plus, if that will define the norm. Okay, so norm, what norm operator is doing, they can take any element from the space. Okay, and they will give one way such that that map to real number. If I have now two real number, if corresponding to this function I have some real number, corresponding to this function I have real number, corresponding to this function I have real number, so I can able to compare. Okay, and I can tell that okay, this function, suppose whatever real number I am getting 2 and here I am getting 3, so this function is more closer than this function. In this way we basically we are able to define. Okay, so norm linear space is nothing but vector space with norm. Okay, now here our space is function space. Okay, so now norm is just able to talk about the length of vector. Okay, so I have function, one function I have selected f1 f2 and fn. I have selected one function and I have clubbed that function in this operator. Okay, so if I club here, then we know that that is going to map to some kind of real number. Okay, so somehow this norm is talking about the length. Okay, and also you can think that is absolute distance from the origin, you can tell. Okay, but most of time if I have to compare two functions, then I need relative distance between two functions or distance between two functions simply. Okay, so distance is defined like this. Okay, so that is just generalization of the classical way to measure the distance. Suppose that I have on real line, one dimensional line, and a and b is there. So in order to measure distance from here to here, what basically we are doing, we are writing a minus 0 and we are using the notion of absolute value. Suppose if we are here, again what we will do, we will write like this. Okay, so distance is always positive. Suppose I have to measure distance between this and this, then I will take this kind of operator. Okay, so now I have to measure the distance in higher dimensional space. Okay, so in higher dimensional space, then what we will do, we will just actually substitute this absolute value by the norm. Okay, and by defining the proper norm, I can tell that in this way I can able to know that two functions are close or not. Okay, so for the standard dot product norm, we recover the usual notion of distance. It means that what I mean to tell, that if I will take x, v is, suppose that x1 x2 you can take, suppose finite dimensional space, and w is w1 w2, and if you interpret this using the standard dot product, then I have distance like x1 minus x2 square plus y1 minus y2 square root of that, like that. Okay, so even if I talk about distance, they will satisfy all the property. Okay, so length will satisfy all three property, and distance, even if you will define they will also satisfy all three property. Okay, so due to that reason I have written one more thing. Just as the distance between vectors measure how close they are to each other, keeping in mind that measure the proximity depend on the underlying choice of node. Okay, so what I mean to say, so I can able to define norm in different way. Okay, we have just seen that whenever I have finite dimensional space, then I can able to define norm LP like this: xi power p and 1 by p I equal to 1 to n. Okay, you can see that now I can substitute p from 0 to infinity, any value from 0 to infinity. So in finite many way I can able to define distance, and that will satisfy, or length, and that will satisfy this kind of notion. Okay, so now I have infinite choice, and due to that reason, if you try to measure the distance between two quantity, then whatever number that comes into picture, that is different. Okay, so suppose that you have point A and B. If you are going to measure in millimeter, then numbers comes into picture, that is different. centimeter, then numbers comes into picture, that is different. So I have different way to measure the distance. Similarly, distance, generalization of distance is nothing but the difference of norm, and due to that reason again I have infinite choice. Okay, and whatever norm I am going to use, whatever scale we are going to use, based on that scale the story of nearness or a story of proximity is different. Okay, and in this way we are also able to measure the distance between two functions. Okay, so with help of norm, okay, we are now able to define the nearness of two functions. Okay, so during school time we are just calculating the distance between 2 points, suppose x1 x2 and y1 y2. Okay, and using the Euclidean norm x1 x2 square plus y1 y2 square, we are measuring the distance. Now I have functions. Okay, so with help of some standard norm I can able to define, even if this is function f1 f2, I can able to measure the distance. So this point is basically highlighting that particular point. Okay, sometime one more important thing is called topology. Okay, so what basically topology is telling, that sometime I have some kind of geometrical object. Okay, so I want to know that two geometrical objects are near to each other or not. Okay, if we are trying to see the nearness of two geometrical object, okay, so at that time we are not going to get some kind of number, some kind of numeric distance, but still I can able to talk about the nearness between two geometrical space. Again norm play a very important role. Okay, so topology, whenever we are talking about topology, so at that time we are talking about some kind of geometrical space, and at that time we are able to define limit, continuity and connectedness, these kind of things. Okay, so basically topology is not going to involve in our problem, so there is no need to worry about that. Okay, so what we have seen here, that with help of norm I can able to define the distance. Okay, and distance is talking about the closeness. Okay, so closeness, whenever we are talking about closeness, I can able to talk about closeness in two way. Either some numerical quantity comes into picture, and in sometime we are not worrying about the numerical quantity, then also we are able to talk about the distance between those two, means those two functions. Okay, so if numeric value comes into picture, at that time we are in non-linear space, we are not going to talk about the topology. If we are not interested in numeric, some kind of numerical value, at that time we are concentrated on the topological space. Okay, at that time we are just defining the point and neighborhood, and after that we are going to do play with open set and closed set, and then we are going to define everything. Okay, in this way norm and topology are related. Okay, so we have two different approach to measure the distance. Okay, in first approach I will take some kind of norm, a standard norm, and we are concentrated on the numeric distance. Another way I will consider the point, okay, and some neighborhood, closed set and open set, and then I can talk about the closeness. Okay, so that is the topic of the topology. Okay, so in this particular lecture or particular course we are going to talk about numeric quantity. Okay, and due to that reason we have to see how basically one can define the numeric distance with help of norm. Okay, now let us come to the some kind of norm in this infinite dimensional space. It means that functional space we are going to consider. Okay, so functional space, what we have seen, that whenever we are talking about function space, not functional space, function space, so in function space element is in form of some kind of function. Okay, and what we have seen, that in order to define f1 I need some kind of interval. So you can see here what I am telling, c0 means some kind, I am just assuming that this function is continuous. I am not assuming that this is continuously differentiable, just continuity condition I have assumed. And here this function f1 means each element of this function space, okay, so that is continuous and that is going to take value from a to b. Okay, Rn means after putting the a and b here, whatever things that comes into picture, that is some kind of real number. So real number is coming here, real number is coming here, same like Euclidean space you can think. Okay, now if we are going to define the norm, so all three properties should satisfy. Okay, so first property is positivity. Okay, now one more important thing I am going to highlight here, that whenever we are going to define the norm of some function, okay, I know that how to calculate absolute value. Okay, so we are going to take help of absolute value only to calculate or to define any norm. Okay, then suppose you have to develop some kind of machine. Okay, so at that time if you know how to calculate absolute value, then that is enough to calculate the norm, even if I have some kind of space where real numbers are involved, a space where functions are involved, polynomials are involved. Okay, so I can able to manipulate that. Okay, and due to that reason it is possible to show that whenever we are defining any norm, we are just going to take help of the absolute value only. Okay, so here you can see that I have defined norm or length of some vector. Okay, so I have taken vector from this space, function space. Now I am going to talk about the length of the vector. So and whenever we are going to talk about the length, we have to make sure that length should be always positive. So suppose that if you take the absolute value, so absolute value of any quantity is always positive. Okay, and due to that reason what happens, that this is always positive. Okay, so suppose I have this kind of function, so I will take absolute value of each and everything, and after that what I am going to do, whatever maximum, okay, f1 is maximum, then I will collect f1. If f2 is maximum, then I will collect f2. Fn is maximum, then I will collect fn. Okay, so in this way I can able to define this norm, and due to that reason this symbol is nothing but Euclidean norm. What does it mean? That once you give value of x between a to b, then what happens, some numbers comes into picture. Here f1, some number is going to generate. So suppose some number 5 is generated here, 6 is generated here, 7 is generated. So now you can see here that after substituting a and b, what happens, that now I have number. Okay, so I have to just select the maxima, same like the Euclidean norm. Okay, and due to that reason we have written like this. Anyone has confusion in this representation, then please let me know. What basically we are telling, that if you have some kind of a space where element in form of functions, so you can write each and every element, you can substitute their argument, you can calculate their value, and after that you have to select the maximum value only. Okay, so in that way I can able to define the zero norm, and this is also called L infinity norm. Okay, similarly if you replace this maxima by supremum, okay, so what happens, suppose that if you have some kind of real number, real line, so and if you are talking about interval, so a and b, so if interval like a and b, and if a and b is included, okay, so I can able to talk that okay, 2 and 3, in this interval 3 is the maxima, 2 is the minima. But suppose if I have this kind of situation, okay, I can not able to talk about maxima and minima. Okay, but I know that each and every element of this particular interval that is less than 3. Okay, so we are giving some another name that is called supremum. Okay, and similarly suppose if I have this kind of situation, so maxima and minima will not exist, but supremum and infimum will exist, like that. Okay, now another choice of norm. Okay, so you can see here that whenever we are selecting norm, then three condition will satisfy. So first condition, positivity is satisfied. Second condition, if you scale it out by each and everything by alpha, it is possible to show that again alpha comes into picture. Okay, so that is also satisfied. third property is triangular inequality. So triangular inequality is also satisfied because numbers are satisfying the triangular inequality, like that. Okay, because underlining things we have just again somehow mapped to Euclidean norm. Okay, so all property will satisfy, and due to that reason this is valid candidature for the norm. Similarly, I can able to define another norm. Okay, that is called now one norm. Okay, so in order to define one norm, I have taken one more assumption. You can see here, in order to define one norm, I am assuming that whatever function element of this function, that should be differentiable, otherwise I cannot able to define this kind of y dash. Okay, so one can define one norm like this. Suppose ck here comes into picture, then I can add more term. Again, that will satisfy all kind of property of the norm. And more general, same like the finite dimensional space. So finite dimensional space, we are defining norm with help of the summation. Now in infinite dimensional space, that summation is actually modified to continuous integration. Okay, here I equal to 1 to n, here that is from the interval a to b. Okay, xp, so again absolute value, so p and everything remains the same. So in this way we are defining the LP norm whenever I have some kind of function space. Okay, so if you see the optimization problem, so most of time either we are defining zero norm or one norm. Okay, and a space, we are considering this space or this space. Okay, every function in this space is continuous. In this space, that is one time continuously differentiable. Okay, anyone has confusion? In this way we are actually selecting norm from the function space, okay, to talk about the nearness. Okay, so length, we know how to define the length of some function. Now if I know how to define the length, then I can also able to define the distance. Okay, just you can club that that into the norm. Okay, now let us come to the another notion, that is notion of convergence. Okay, what we have seen that, suppose I am solving the some kind of extremization problem. Okay, so suppose if this function is going to minimize this functional. Okay, so whatever value that is going to comes into picture, that should be least. Okay, it means that I will start anywhere, okay, in this local neighborhood of this particular quantity. Finally I have to convert somewhere. Okay, and due to that reason some notion of convergence comes into picture. So here sequence xi, so here xi, you can assume that I have some kind of function. Okay, and function now are in a space. So now you can see that, now what I am going to do, I am going to see the how function is basically changing, and finally I have to make sure that that is converged to this function. Okay, so how basically we are defining convergence. So suppose you have some kind of sequence. Okay, so sequence, we are defining xi, some quantity I equal to 0 to infinity. Okay, so I equal to 1 2 3 4 up to n. So that is called sequence. Okay, so suppose some kind of sequence in this norm linear space. Okay, so norm linear space means now I have a space, I know how to operate on a space, how to define the proximity. Okay, now what I am telling, that some sequence is converged to some point. If this condition is satisfied, it means that for every epsilon I select one epsilon, and suppose if x0 is converging point, so if you select any sequence xi from this space x, that is going to converge to x0. Okay, for I greater than equal to some number n. Okay, and I can select in function of epsilon. So you are able to select epsilon equal to 0 also. Okay, so if epsilon is very small, then xi equal to x0. Okay, so in this way I can able to define the concept of limit in higher dimensional space. Okay, in one dimension we know that how to define the limit, because in one dimension I have to approach only from two sides. Okay, but in higher dimensional space, now I have to approach from all sides, and due to that reason notion of ball is required in order to define the convergence. Okay, and if some sequence is converge, then their limit is unique. So whenever you have to prove uniqueness, then you can assume that this sequence, I have taken two sequence in this space, and one is going to converge at x, another is going to converge to y. Okay, and now you can just show that x is y. So it is possible to show that if I will calculate x minus y, so I can, and if I add xn and remove xn, so I have x minus xn and xn minus y, and we know that xn is going to converge to x and xn is going to converge to y. Due to that reason, this is 0. So x minus y equal to 0, so only I have one choice. In this way, we can also able to give guarantee that if sequence is going to converge, then limit is unique. Okay, now what happens, that what we have seen here, that in order to check that I have some kind of limit point or accumulation point, I need the information of accumulation point. Okay, it means that suppose I have to solve the minimization problem, so I know that function at what point basically function has minima, what point function has maxima. So this point is known, but that is not the case always, and due to that reason I need some kind of condition where without knowing the limit I can talk about some kind of convergence. Okay, and now that sequence, okay, so now what different sequence, so one I have one sequence in the space, means function space I have considered. Okay, and I know that how to define the convergence. If I know the limit, I can tell that for every epsilon greater than 0 there exists some kind of natural number n, that is function of epsilon, and I have to just check, I can take any sequence and I have to just show that that is less than epsilon for all n equal to, that is function of epsilon. Okay, so for all n, and this is greater than, I is greater than n, so we have to just show this. Okay, so if I know this, then by numerical, just by opening this norm I can able to show. Okay, but suppose if I don't know x0. Okay, so what this sequence is telling, you can take any two sequence in the space. Okay, and after that, now what we have to check, again I have to check the same condition between two sequence. Now I don't know the limiting point or accumulation point, due to that reason I have taken xn and xm, two sequence from the same space. Now again I have formulated one ball epsilon, so distance between these two, so we have to show that for all n and m, basically xn minus xm is less than epsilon. Okay, so it means that meaning of Cauchy sequence is that if you consider any two sequence in the space, okay, then that is going to converge towards each other. Okay, and it is possible to show that if I have convergent sequence, convergent means if I know the limit, okay, then, and if I select any epsilon, then I can able to define n. Okay, if I further decrease epsilon, again I am able to define some n. Okay, and in this way I can able to decrease epsilon to 0. Okay, so now if I have convergent sequence, it is possible to show that that is also Cauchy, because all convergent sequence is going to converge towards same limit point, because limit point is unique, and due to that reason if you check the distance between any two, that is converged. Okay, so mathematically you can see that xn minus xm, now I know the limiting point, so xn minus x minus xm, I have added x, and x is the accumulation point, and after that I can able to use the triangular inequality or normal inequality, you can tell. And again, since xn is tending towards x and x is tending towards xm, because this is convergent sequence. Okay, so I have some kind of a space, non-linear space, and I know that that is in that space convergent sequence exists. It means that any sequence is going to converge to the limit, so limit point exists. So I can, if a limit point exists, means if I select any convergent sequence, that is going to converge to that limit. Okay, and due to that reason I have selected two different sequence xm or xn, so that is going to converge to x, and that is tending towards 0. But reverse is not true. Suppose now if two things are converging towards each other, it might possible that will not converge to the limit point. Okay, so there exists some kind of space where I have some kind of Cauchy sequence, means any two sequence will converge, but that is not going to converge to the limit point. Okay, and due to that reason, now we have some kind of notion that is called complete space. So in complete space, it is possible to show that Cauchy sequence also has a limit. Okay, so I have two different space. It might possible that Cauchy sequence is convergent, or second option is that Cauchy sequence is not convergent. Okay, so I am going to select those kind of space where Cauchy sequence is also convergent. It means that if even if I don't know the limit, I can take any two point two sequence, and finally that is going to converge to the limit point only. That is the benefit. And due to that reason, one space that we have given very special name to one space, that is called Banach space. Okay, so let us try to see the definition. So definition of Banach space: a norm linear space. It means that I have some kind of a space with some kind of norm. Okay, so I can able to define the closeness, that is the requirement of norm. So X is complete if every Cauchy sequence X has a limit in X. Okay, it means that if I take any two Cauchy sequence, that is going to converge to some point, and that point is automatically is the limit point. So even if I don't know the limit, okay, but if I take any two convergent sequence, I can able to find that particular limit point. Okay, and that space is called Banach space. Okay, and most of time whenever we are solving the optimization problem, okay, we don't know the maxima and minima. Okay, so I don't know the accumulation point. Okay, and due to that reason, whatever space I am going to consider in this particular course, that is Banach space. Okay, it means that if I will take any two sequence, okay, that is going to converge to the limit point if limit point exists. Okay, so that kind of requirement I have whenever we are going to solve the optimization problem, particularly in infinite dimensional optimization problem. So same kind of things I have written. When seeking an optimal vector, maximizing or minimizing a given objective, we often construct a sequence of vector, each number of which is superior to the preceding number. Since we are talking about maximization, it means that I have constructed some number. Suppose even if you can consider the finite dimensional problem or infinite dimensional problem. So I have to make sure that whatever function that is going to club here, and so suppose this is maximum or extremum point. So this should be maximum because that is going to map to some real number. So I can able to compare. Okay. So due to that reason, I have written construct a sequence of vector. Vector is here function. Okay. So vector may be function, maybe column vectors, maybe some kind of matrices. Okay, so here in optimization problem our vector is function. Okay, so each member of which is superior to the preceding member, the desired optimal vector is then the limit of the sequence. In order to the scheme in order that the scheme is effective, there must be available a test of convergence which can be applied when limit is unknown. Okay, so even if limit is unknown, and if I know that there our space is complete, means Banach space, then I can able to solve the optimization problem. Okay, so what is the story up to this point? I know that my space contain the functions. Okay, I have two different requirement. I am assuming that function is continuous or continuously differentiable. Okay, after that I know that how to define the distance inside the space. Okay, and third thing, whatever space I am going to consider, that is Banach space. In this way, even if I don't know the optimization point, but I can able to apply the algorithm. Okay, now you may be surprised that is there exists some kind of a space which is incomplete, means there exists a Cauchy sequence but that is not convergent. It is possible to construct. Okay, if you define norm like this, okay, it is possible to show that if you consider this sequence. Okay, so you can see that a story is very interesting. What they are telling, that you can consider any sequence. If any sequence become fail, then whole things collapse. Okay, and due to that reason I have considered some kind of a space of continuous function. I have defined that function from 0 to a. You can define from any between any two numbers a to b. Okay. Now it is possible to show that if you take this kind of sequence, and if you define xn and xm, so that is going to tending towards 0. Okay, but this sequence is not going to converge anywhere. Okay, and due to that reason, if you have continuous some kind of continuous function defining limit from defining between 0 to a this interval, and if you select this kind of norm, okay, then you are losing the Banach space. Okay, and due to that reason this norm is not preferable. Okay, you might have seen that whenever I am defining the 0 norm in this space, at that time we are defining maximum over a to b, and after that something like x. Okay, I am not defining like this. This is the region. Okay, now you are able to construct several incomplete actually space, non space. So if you define some kind of sequence like this, okay, it is possible to show. And suppose if you define norm like this, maximum zeta I, again it is possible to show that this is Cauchy sequence, but that is not the convergent. Please check by yourself. Okay, now you have to just do the numerical calculation. Okay, I have written everything. Okay, now it is possible to show that a Cauchy sequence is bounded. Okay, and proof is again very easy, because whenever we are talking about Cauchy sequence, then I have to make sure that any two sequence that is less than epsilon I have selected 1. You can select any number n greater than n, then xn I can able to write, and that is bounded by this. Okay, so if this is always bounded, okay, because I have selected some kind of specific and a specific sequence I know, so due to that reason this is always bounded. So this is the story of the Cauchy sequence. It is possible to show that if I will take some kind of a space C01, and if I will define norm in a standard way, then that is Banach space. Okay, so proof is again not interesting for us, so I am going to skip this proof. Okay. And what basically here we are telling transformation, what happens that people has defined first vector space. Okay, and in order to define vector space, what they have done, they have considered some kind of a space and two different kind of operation, vector addition and scalar multiplication. After that they are telling that suppose if I have two different space, so what kind of transformation I will use such that this is also vector space and this is also vector space. Okay, and if that is the so, then they are telling that as a some kind of transformation. Okay, some kind of function you can take. So x and y are linear vector space, and D is the subset of x. You can select D. A rule which associate every D to element y is said to be transformation. Okay, and it is possible to show that functional is also some kind of transformation from function space to some kind of real space where everything is represented by real number. Okay, so real space you can tell. Okay, so again that is the function. So that this is the message of this particular slide, and you are able to define the continuity also. Okay, so basically whenever we are defining the continuity, so suppose I know I have to define that some function t that is continuous here. Okay, so how to define continuity? First, what you can do, that you can enlarge it, okay, stretch it, okay, and after that it means that you have to stretch this, and by stitching this, if this point is not separated, okay, so suppose tx minus t0, this stretching you can define as epsilon. So this point is, if that is going to live inside the delta ball, then we can define that for every epsilon there exists a delta, such that if this kind of relation is satisfied, then we are telling that this point, at this point means this particular function is continuous. Okay, so continuity, whenever we are defining the continuity, at that time again we are considering two different ball. Okay, one ball we are associated at this point. Okay, so suppose, think like this, suppose you have x and after that I have tx, so tx is the output. Okay, so what we are going to do, I am going to stretch the tx. Okay, so after stretching this I have to make sure that x, whatever argument, that is not stretched out much. Okay, and due to that reason, in this way I can able to define the continuity. Okay, so again again continuity is required. Okay, because several time I am telling that this function is continuous, this function is continuous, so if you check the space, then that will satisfy this kind of property. Okay, now let us come to the local minima. Okay, now what happens, we are able to identify the space. Okay, so we know that our space is infinite dimensional space. Okay, and each and every element on this space is in form of function. Okay, after that we know that how to define the closeness in this space using the help of norm. Okay, and I have already told you that I am going to consider the zero norm or one norm. Okay, I have defined what is meaning of zero norm and one norm in function space. Okay, and after that I have defined some kind of transformation. Okay, where what happens, function space, so I have j, and if that is function, then that is mapped back to some kind of real number. Okay, so functional, so now I am able to compare this real number. Okay, so meaning of local minima, a function y star belongs to A is a local minima of j over A if there exists epsilon and and if this relation will satisfy. Okay, so what I mean to say, suppose that you have three functions and that is going to minimize some kind of functional. Okay, so what you can do, if this is minima or maxima. Okay, so suppose that here I am just talking about minima. So what happens if you see the neighborhood of this? Okay, so value of this is always less than all the value of this neighborhood. Okay, so using norm I can able to define the neighborhood, and by defining neighborhood I can going to put the value, and after that if I am going to compare it, if this relation will satisfy for all y and y star, then I can tell, or at least for all y belongs to A, then I can tell that y star is local minima for that particular functional. Okay, so in this way, by identifying the space, norm, and after that after that vicinity, we are able to talk about the local minima. Okay, so now it is time to conclude the today's lecture. Okay, so today's lecture is a little bit longer. Okay, so what we have seen, that whenever we are talking about infinite dimensional optimization problem, it might possible several new concepts is actually I have covered in one class, so that is difficult for the several newcomers which are not actually knowing the vector space or linear algebra. Okay, but slowly you have to become familiar, because whenever you are going to solve any problem, these kind of concept involved, means concept of vector space, concept of linear dependence, independence, basis, these kind of things will involve. Okay, after that, every time whenever you are going to solve some problem, you have to map from higher dimensional space to one dimension, because in a higher dimension you cannot able to compare. Okay, so you have to know some kind of way such that I can able to transfer from higher dimension space to one dimension. Okay, and for that notion of norm is required. Okay, so what we have seen, that in order to solve some kind of means optimization problem in infinite dimensional space, what kind of requirement I have. Okay, first I have to identify the space carefully. Okay, identifying a space carefully means I have to see the regularity condition on the functions. Okay, after that I have to define nearness. Okay, so for that I need norm. I have several choice of norm, so any one choice of norm is okay, but you have to make sure that whatever space you are going to consider, that is Banach space. Okay, otherwise, if since maxima or extremum point is not known to you, then if you take any two sequence, that is not going to converge to that particular limit, and due to that reason you have to consider that space as a Banach space. Okay, and after that, if a story is that, then you have to map that function using some kind of transformation to functional. Okay, and just you have to check the inequality. If that inequality is satisfied for all A, okay, then we are telling that y star is the local minima in that particular vector space. Okay, in this way we are solving the local local means extremization problem of the infinite dimensional in infinite dimensional space. Okay, so now actually session is open for the question, so if you have any question, then please let me know. Any question?
Sir, yes, I have a question.
Okay, please go ahead.
Sir, in a zero norm,
Okay,
how can we satisfy the triangular property?
so okay, let us come here. That is very easy to show.
Yes, sir.
Here you can see that what is meaning of the triangular inequality. We are telling that suppose if I have some quantity, okay, let us first come to the triangular inequality, and then we will apply this kind of, then things become okay. Here you can see x plus y, that is less than equal to norm x plus norm y. Okay, and how basically we have defined the norm? We have defined norm x, this is zero norm, that is maximum a x and b, and after that I have xt. Okay, like this, t is here, something like that. Now what you can do, in place of x you can replace x plus y. So if you replace x plus y here, then what happens, again I have maximum a t to b, and here x plus y, something like that. Okay, now you can see here that if I have, here I have absolute value again. So what we have to do now, I have here not absolute, I have Euclidean norm. Okay, this is representing the Euclidean norm. So what I will do now, I have some kind of function. So function has f1, f2, f3 or fn. Another function you can take, that f dash 1, f f2 dash, f3 dash, and f4 dash. Okay, so here this is nothing but x, this is nothing but y. Okay, now suppose if I apply this operator max, so is it possible to write this or not? Max a directly I will write, and after that we will check. That is also easy. Priyanka, is it possible to write like this or not?
Yes, sir.
And what is the definition for this? What is the definition of this?
Sir,
From
maximum value of the magnitude of x and
is x I have already defined. Okay, and this is
yes.
y. Okay, so x plus y will satisfy this. Any confusion?
Okay. No, sir.
So in
It's
this way
clear.
we are able to check that triangular property is satisfied or not. Okay, because
Okay.
finally if even if we are dealing with functions, okay, and if I am going to keep the value, okay, value of this
Sir,
function, so function between a to b generates some kind of number, so I am just adding two numbers. Okay, so
okay.
and I know
Sir,
for two numbers that addition of two numbers is less than equal to addition of this, so that property is always satisfied. Due to that reason I can write like this.
okay, okay, sir.
So finally, function is also going to map to some number only. Okay, and number will satisfy the triangular inequality property. So due to that reason, this property is obvious.
Okay, sir.
Any other confusion? Okay, if you don't have confusion, then I am going to end the today's lecture.